This is my lecture 12. So in the last class we saw that because of sampling, the stability of a feedback system reduces, and you have to choose a suitable sampling time to have the desired system performance. That we will see in this class, how to choose that. But so the digital control system, as I said at the beginning, so there are digital control. One is sample data control systems, another is discrete time control system. So sample data control system, so there as I said, that the plant is continuous time, but the controller is implemented in digitally. But it may happen that the whole thing is in discrete time domain. That means plant is also discrete time plant. So whether that kind of discrete time systems exist or not. So examples of discrete time, pure discrete time systems. So examples of discrete time systems. So sample data system exists always exists because the plants are continuous time domain, and the controller is implemented in a digital fashion. So sampling is involved. So the sample data system. But if it is now the question is whether a system can be pure discrete. That means plant is discrete time plant, controller is also discrete. So such kind of things, such kind of physical systems are there or not. So one very interesting example is interest payment system. Banking in bank, the interest payment system. Interest payment system. So this is a pure discrete time system that we'll see. So what is the problem? Problem is let one a P0. What is the interest payment system that is in bank? Suppose you are taking, you are borrowing capital, some capital initially, and then the interest on the unpaid balance. That means interest on the capital, the principal, and the interest on the principal is say R. Interest rate, annual interest rate is R, and the number of and the amount of installment that you will pay is U per year. So then we can have a relationship between the amount owed after say some period of time with the interest rate and the installment. We can have a we can model this system, interest payment system, in a discrete time framework. So how you can do it, that we'll see. So P naught be the capital borrowed, initially. So discrete time, that's why the discrete time control, discrete time systems are very good in application in banking system, in economics. So P naught with the capital borrowed initially. Okay. B. So R be the interest rate. R be the interest rate. R be the interest rate on unpaid balance per period. C. U be the UK, say well, u be the installment to be paid per period. Okay, every period, yearly, monthly, whatever it is. D PK denote the amount owed after kth instant, kth period. Okay, so now we have to model this the interest payments. So now if you see that what is the installment you have paid at 0th year, that means at the time of starting you have paid installment u0. So after 1 year, say how much installment you have to pay, how much amount that will be owed. So then what is P1? So P0 is so in the first year how much you have borrowed? In the first year you have borrowed is P0. And then how much you have installment you have paid in the first year itself, then 0th year, the beginning you not say. Okay, and then in the next year, then in the next year how much amount you will owe? 1 plus r into this much. That means r into, yeah, so it will be 1 plus r into, r is the interest rate, so it will be 1 plus r into P0 minus P0. So in this way, in general what will happen? In general, Pk plus 1 will be 1 plus r into Pk minus u of k. Okay, so this can be, so if you take this, if you take Z transformation, then it will be Z into Pz minus Z P0 equal to 1 plus r into Pz minus Uz. So interestingly, this can be represented in this feedback form. So this can be represented in terms of a nice feedback form. You can see, so this is your, suppose Uz, that is the amount of installment you will pay, and then this is minus Uz, then it will be plus, this is your Pz into 1 plus r, okay, into 1 plus r, then 1 by z, then your minus P0 minus or plus 1 by this will be this will be P, this will be Pz, yeah, let us see, then what will come? This will be your Pz. So Pz minus z divided by, so this should be minus. Okay, so this is the feedback system. Pz, this is your plus, this is plus, so this is your plus, this is a plus, this is minus. So that means Pz minus P0 into 1 by z, no, So pz minus uz into 1 plus r into 1 by z. Oh, here this side if you bring, then it will be p plus p naught. This would be equal to pz. So now suppose so the whole this interest payment system you can represent in terms of this block diagram. Now what is the problem? Problem is, suppose in a banking system the problem may be like this: to find a constant uk uk say gamma say constant uk such that pn equal to 0 for a given p naught. That means what? Suppose you have taken some capital, you have borrowed some capital from a bank, and you are paying installment every year, say gamma, every year starting from the beginning, 0th year, first year, second year, like that. Now what I want, what is the amount of installment that you have to give, so that after nth year, just at the nth year, what will happen at the nth year? So you will not so you will not have any amount that will be that you have to pay to the bank. Okay, that means the amount owed to the bank will at nth year will be 0. Okay, so that means you have to how to find this. You have to solve this block diagram, and if you if you take the discrete, if you use this equation and if you solve for it, then you have to take the inverse Z transformation and all these things. So this is a very good application, and you can find, just I am not doing this here. So the answer, just I am writing gamma will be equal to, just I have found it, 1 plus r. This is a very interesting problem. N minus 1 into p naught divided by 1 plus r to the power n minus 1. Okay. For example, you want to solve, you want to clear your capital that is borrowed. You have bank just within 1 year, just by 1 year. So n will be equal to 1. So n will be equal to 1. In that case, n will be equal to 1. If you so how much installment you have to pay? Whatever amount you have borrowed, that is gamma will be in that case equal to p naught. That is correct. Okay, so this is so this I am not solving, so I am just suggesting you check it, solve the just I'm writing check it. So you can solve it easily, because this is your discrete time system. This is a discrete time equation. So you can from here what will you get? You just divide you just get your pz pk. What is the solution? Inverse Z transformation of pk. Pk you get in terms of say uk equal to uk you can fix at say gamma, uk equal to gamma. So uk will be constant. Then you find what is an expression for pk. Then you put in terms of in place of k, you put just n equal to maybe k equal to n. Then you will get this expression. Gamma will come out with this one. So this is not so. Just you have to take inverse Z transformation here. Okay. So some other examples of discrete time system is, say, a discrete time PID controller. That is also widely used. That's why I will just say what is discrete time PI and PID controller. So discrete time PI stroke PID controllers. So PI controller first say PI controller. What will you, so PI controller, as you know, what is the controller? UT equal to KP into ET, that is the tracking error, E is R minus Y plus KI into 0 to T ET dt. So it is in continuous time domain. So this is in continuous time domain. Okay, so this just if you put T equal to KT here, if you put T equal to KT, then what will you get? You get equal to KP into EKT plus KI 0 to KT EKT. Oh, sorry, this is your this is a T is a dummy variable, so here T you just keep, that is not the problem into. So this is T because here I have put already T, so this is here. Or tau also you can put, that is not the big issue. So then from here you will get, just if you put now you in place of K, if you put K minus 1, say K minus 1 upper bar means it is a bracket, first bracket K minus 1 into T. So this is equal to Kp into E of K minus 1 T plus Ki into 0 to K minus 1 T into Et dt. Okay. Then now if you subtract these two equations, U kt minus U of K minus 1 T, then what will you get? This will give you Kp into EKT minus E of K minus 1 into T plus Ki into integration of 0 to Kt E T dt minus integration 0 to K minus 1 T into Et dt. So this will imply what? This will imply U of Kt minus U of K minus 1 into T. This is equal to Kp into, so the my ultimate objective is to obtain a digital version of discrete time version of this PI controller. PI controller is widely used in industry, that's why I am trying to make it a discrete time version so that you can implement it digitally. So K minus 1 into T equal to Kp into E of Kt minus E of K minus 1 into T plus, so what is this difference of integration? It will be Ki into K minus 1 T into Kt Et dt. So this can be written, so using rectangular rule, so this integration will become what? This integration will be just equal to Ki. This integration will be just equal to Ki into T into Ekt. Okay, so using rectangular rule, what you can get? Using rectangular rule, so Ukt minus U of K minus 1 into T, this is approximately equal to Kp into Ekt minus E of K minus 1 into T plus Ki into T into Ekt. So this is this is the main step. This this you can approximate to ki into t into ekt using rectangular rule. So that means the integration from k minus 1 t to k to et dt. So the area will be just ki into difference between the two into that value of this one at kt. So this will give you what? Now if you take the z transformation, uz minus z inverse into uz, this is equal to kp into approximately, I am just writing equal here, although for my convenience, uz minus z inverse ez plus ki into t e of z. Okay, so this implies 1 minus z inverse into uz z. This is equal to kp plus t into ki minus kp into z inverse into ez. So this will give you ultimately your, what is the equation? You will get uz by your ez. So you will get ultimately uz by ez. That is the transfer function. Ez is input 1 degree of freedom PI controller. 2 degree of freedom PI controllers are also there. So in that case, the KP you can place in the feedback path. That is minor loop implementation kind of thing you can do. Integrator you can put in the forward path. That I am not considering. That is also called IP controller. So uz divided by ez. So this is equal to your z into. So if you take this will be z into kp plus tki minus kp divided by z minus 1. So this will ultimately give you uz by ez. This is equal to kp plus tz. Yes, it will be z minus 1. So kp plus tz into ki divided by z minus 1. So this is your cz. That means this will ultimately give you what is your cz. That means controller transfer function cz equal to kp plus tz by z minus 1 into ki. So here, so this is very important. This is your PI controller in this. So discrete time PI controller. Discrete time PI controller. This is discrete time. This is your discrete time PI controller. So similarly, in the same way, you can also obtain the PID. For example, this is your PI. So similarly, you can get say PID controller in discrete time. PID controller in discrete time will be like this. CZ will be. Please check it. I am not writing and not proving it. So ki into this one will remain same, tz by z minus 1 plus kd into z minus 1 by z minus 1 by tz. So t is your sampling time. So t is sampling time. Okay. So this is your PID controller. So we have seen that there are a pure discrete time system exists like discrete time, that means interest payment system in bank, or discrete time PI controller, discrete time PID controller. So discrete time systems exist, particularly the interest payment system. So in banking system, that in banking system, different processes in banking system, different processes in economics, you can model as in terms of discrete time system, and their feedback control plays an important role. Stability and all these issues are there. So control system has very good application in digital control, has very good discrete time control, has very good application in banking system and economics. So now we will come to our final topic, that is digital, that means controller design. So approaches to digital controller design, that is the final part of this course. So approaches to digital controller design. So before that, I just want to say here, although I have not said, I think, so given a transfer function in discrete domain, say, you can obtain its impulse response or step response in a similar way as you have in case of Laplace transform. In case of continuous time system, we have used inverse Laplace transformation, and we have used partial fraction expansion, and all these things. So here also we'll use just Z transformation. It's an inverse Z transformation, and the approach is same. Just the standard Z transformation formula will apply as we have used for Laplace transform also to obtain Z transformation. For example, if you are given a plan, say Z by Z minus A, so what will be its impulse response? Impulse response will be A to the power K. So if you are given a transfer function in product form, okay, so you have to bring so you have to transform that, you have to bring the system using partial fraction expansion to the standard form, standard Z transform, standard Z transformation form, so that you can, the existing results of Z transformation, some standard functions you can apply. Okay, so that I am not going into detail, so you can easily do it. That is not, there is nothing is there, just same as inverse Z transform, inverse Laplace transform. Here you have to do inverse Z transform to get the time response. So now the approaches. So what are the approaches in your digital control? So there are two approach main. So one is, there are two approaches. So one is your translation of analog design. Analog or continuous time system design. So this is also called digital, or it is also called in literature, it is known as digital redesign. Okay. Another way is direct discrete domain design. Direct discrete domain design. So now about one, that means translation of analog design. What is translation of analog design? So here what we do, so one, translation of analog design, analog or continuous time controller. So here we do what we do, so given a continuous time controller, we just obtain a discretized version. We have seen that in case of continuous time, if you suppose for a design for a system for a continuous time system, we have designed some PI controller, and your PI controller transfer function is like this. PI controller transfer function is in continuous time is this one, Kp plus Ki by S. So now in discrete domain, then what will be your transfer function? Kp plus T into Z minus 1 by Z by Z minus 1 into Ki. So now that means only Kp and Ki you have already designed, already found out the gains. Now you have to only choose the K here. So the main steps is T here. So here sampling time. So existing, what is done here, translation of analog design, the existing analog controllers are converted into a discrete time controller. So the sampling time chosen, the sampling time used to discretize, the sampling time, this is very important step. The sampling time, this is the main step. In fact, your continuous time controller is given. Now you have to convert it into equivalent discrete time form or discrete time controller. The sampling time, how will you choose the sampling time? Because to obtain a discretized model, you need a sampling time. So given a controller, how to obtain a discretized model, any arbitrary controller, that I will come. So the sampling time here should be much less. So 10 to 15 times, 10 to 50 times as compared to the closed loop system bandwidth, closed loop continuous time system bandwidth, So that means here the sampling time has to be chosen, the sampling frequency has to be chosen much faster than the bandwidth of the system, at least 10 to 50 times. So here sampling time, sampling time, choice of sampling time when you are discretizing a system, discretizing a continuous time system, sampling time plays an important role. So as per Shannon sampling theorem, the sampling frequency should be at least twice for a low pass behavior of the system. At least should be twice the maximum frequency content of the system, or at least should be twice the bandwidth of the system. But to be in the safe side, it should be at least 10 to 50 times. So we normally take. So otherwise, what will happen? Aliasing effect will happen. That means zeroth order hold that you have used for zeroth order hold that you have used for reconstruction of the sampled signal to its approximate reconstruction of sample signal reconstruction of sampled signal to reconstruction of sampled signal to equivalent analog signal. So then you will see there will be the analog signal that you will be able to reconstruct using zeroth order hold, that will be far away, that will be widely different from the desired one. So the aliasing effect will be there. So I think in digital control class, all those things you have studied. So I'm not going to discuss all those things, sampling theorem and all those things. So sampling theorem plays an important role. So at least should be sampling frequency should be at least 2 times the maximum frequency continuously. Otherwise, zeroth order hold will not be able to reconstruct the sampled signal, reconstruct the continuous time equivalent of the signal. Zero hold signal, continuous time equivalent signal. It will not be able to properly construct. Okay, so that is very important thing in digital signal processing also. Hopefully, you have already studied those things, aliasing effect and all these things. I am not discussing this one, but this you just keep in mind that whenever you are discretizing a continuous time controller or continuous time system, your sampling frequency should be at least 10 to 50 times. But if your sampling frequency is much higher, then what will happen? Approximately you will be converging again towards your continuous time system. Then what is the problem? Then more high speed processor, more high speed ADDA converters, all these things, digital cards and all these things are needed. That is the problem with high sampling frequency. But nowadays, so high frequency sampling is possible because high speed digital processors are there. Anyway, so this is your translation of analog design. Now how to now the question is, given an analog controller, how do you translate? Given any analog controller, for example, we'll do it. So here we'll do it. Say translation of analog design, discretization using bilinear transformation. So bilinear transformation we'll use for discretization purpose. What is bilinear transformation? So bilinear transformation is nothing but the relation between Z and S. So we know what is the relation between Z and S. So far we know when we saw that the relation between Laplace transform and Z transformation, that means variable, then at the time we saw that Z equal to e to the power st. This one we put where t is the sampling time, s is the Laplace variable, s is the Laplace variable, z is the variable for Z transformation. So then from here, what you can do? You can write Z inverse equal to e to the power minus st. So this you can write as Z inverse. Now e to the power minus st can be approximated like this using first order Pardee approximation. So this is your first order. This is nothing but is first order Pardee approximation. So this is the first order Pardee approximation of this one, e to the power minus st. So then from here what you can do? You can take 1 plus Z inverse divided by 1 minus Z inverse will give you what? 2 divided by 1 plus 2 divided by st. So this implies your what? This implies 1 plus Z by 1 minus Z equal to 2 by S into T. So this implies S equal to 2 by T into Z plus 1 divided by Z minus 1. So this is very important relation. This is known as Tustin bilinear transformation. This is known as Tustin's bilinear transformation. So So that means S variable we have represented in terms of a Z. Okay. So if you have a continuous time controller, so CS, so what will you do? Just S will replace by this 2 by T into Z plus 1 by Z minus 1. Then it will be in discrete time domain. So for example, if your system is like this, just one simple example we will consider. Simple example, say your suppose your GS is equal to your 1740 divided by S into 0.25 S plus 1. So we want phase margin, say greater than equal to 45 degree, phase margin equal to 45 degree. Okay, phase margin not greater than equal to, say equal to, say phase margin equal to 45 degree at gain cost of frequency equal to, say 125 radian per second. So design a discrete time lead controller. Design a discrete time controller. Just I will not write lead or lag. Discrete time controller. So this is the question, suppose. So that means specifications are given in continuous time domain, but I have to opt in a discrete time controller. So how will you do that? So you can easily see what is the continuous time controller. So I am not deriving that the continuous time controller will be, just I am directly writing. You just please verify continuous time controller is a lead one. Lead controller will be required, that you can verify. Please check it, all the things I have taught. So the continuous time controller will be a lead controller. So what is that one? So this you can verify. It will be 6.24 into S plus 50 divided by S plus 312. Please check it. So to meet phase margin equal to 45 degree at gain cost of frequency 125. So here no steady state requirement is there. So it is a normalized controller. You can see if you multiply this one, S equal to 0, if you put, it will be 1. That means H0 equal to 1. So the normalized controller will suffice, because here no requirement of on steady state performance is given. So so this is the lead controller to meet this phase margin, this one, and gain cost of frequency, this one. So now it is an analog controller or continuous time domain controller. You have to convert it into discrete time domain. So using, then first what you have to find? We have to find what is the sampling time. So to find T, what will you do? Sampling time. So closed loop bandwidth, you can easily see closed loop bandwidth will be, you can check from this here. So closed loop bandwidth, or you can take approximately this gain cost of frequency also as bandwidth. Anyway, so closed loop bandwidth also you can check for this system using board plot. Closed loop bandwidth. So closed loop bandwidth will be, say 180 radian per second. So that you have to find out. So using MATLAB, you find out using MATLAB. Okay. Or you can take for your, so here although I have taken 180 radian per second, approximately you can take 125 also. That is gain cost of frequency. Closed loop bandwidth is near to gain cost of frequency. So that also you can take. So anyway, I have taken 180 radian per second. So this implies what? T should be less than 1 by 10th times of what is the corresponding time period for this bandwidth. So 2 pi by 180. So T should be T should be then at least 10 times less. Sampling time should be at least 10 times less. The time constant, the period corresponding to the bandwidth. So here what I have written should be 10 to the 15 less as compared to the closed loop. Yeah. Yes, sampling time, sampling frequency I should say, compared to the compared to the time period corresponding to the closed loop, compared to the time period I should write, time period corresponding to the closed loop closed loop or I should write like this. Yeah, time period corresponding to the closed loop continuous time system bandwidth. ठीक. Okay. So now this is your t is less than this one. Then so what is the time period corresponding to your bandwidth? So 2 pi by 180. So how much time period? So what should be sampling time? Sampling time should be less than 1 by 10th of this one. So this implies sampling time should be 0.003 seconds. So on choosing, so if I choose say t equal to 0.001 second, then what will happen? Then your Hz will come out to be Hz. How will you get Hz? So just S equal to you will replace S by 2 by t into z plus 1 by z minus 1. So Hz will be equal to 6.24 into 2 by t into z minus 1 by z plus 1. So here it is z minus 1 by z plus 1, no? So it will be z plus 1, this is z minus 1. It will be z minus 1. Z minus 1 by z plus 1 plus 50 divided by 2yt into z minus 1 by z plus 1 plus 312. Okay, so if you compute this at t equal to 0.001 second, so this will give you Hz equal to 5.5 into z minus 0.95 divided by z minus 0.73. So minus sign means you see it is stable because it is unit circle is the stability region. So please check it. I have already checked. So in this way you can, if you have a if you have an analog controller or continuous time controller, you can directly convert the equivalent digital controller using that is called digital redesign or translation of analog controller. Another thing is that, so another way of designing digital controllers is direct digital design. So direct discrete time design. Two is direct discrete time design. Direct discrete time design. So what is direct discrete time design? So direct discrete time design. Now what you have to do? So there are many methods to direct discrete time design. So one is say a root locus. Root locus. So already I have shown in the last class that how root locus can be used to assess stability study of discrete time system. And there we saw nothing. The same. It is the root locus for discrete time system will be same as continuous time system, except the stability boundary is now the unit circle. That means roots should lie within that unit circle for stability. Another is root locus. You can directly use lag lead controller. Also, you can design lag lead controller. Here some method is also there, and more important is pole placement. So pole placement method and root locus method it is unchanged. Okay, so these two will be unchanged. Okay, and lag lead and lag lead controller, these two remains unchanged, means root locus, as I said, the boundary will be just unit circle, and pole placement just is in terms of now all the things will be in terms of closed loop pole polynomial, and all the things will be in terms of Z domain. Now the poles you have to choose properly. Poles you have to choose in the right side of the unit circle. Why right side of unit circle? I have already explained in the last class. So pole placement and root locus will remain same, direct extension of your continuous time design. And in case of lag lead and lag lead controller design is little bit involved. Involved means all the rules will be same, but here the board plot, when you will do board plot, will be little bit different, because in case of discrete time system, Bode plot will not be same as this one. Board plot, when you will do, just in case of frequency response, you are changing frequencies from 0 to say infinity, very high value. So here you need not to do. In case of discrete time system, frequency you need to change from 0 to only pi only. So then again pi to 2 pi, your the same performance, same thing will be repeated, because here your in case of frequency response, or in discrete time system, mod g is mod gz. When you do gz, means z you have to replace by e to the power of st, then s equal to j omega you have to put, and then you will see here because of the periodicity of e to the power of j omega. Here you need not to compute, you need not to do for omega equal to 0 to infinity. In Nyquist plot also you have to go from omega to pi, then pi to 2 pi. So omega to pi, in case of Nyquist plot, omega equal to 0 to pi will be, that means the 0 to pi will be one plot, and then pi to 2 pi will be mirror image of 0 to pi, and then again 2 pi to 0 will be infinite semicircular arc, like that. So here only in case of lag lead controller or board plot, gz you have to replace by g into lz, that means loop transfer function. In place of z you have to replace z by e to the power of j omega t. So just I am writing for board plot of LZ in discrete domain, digital controller, discrete time system, in discrete domain, LZ only you have to replace by L into Z equal to e to the power st. That means L into e to the power of j omega t. Okay, so now you can see, so Lz equal to Lj omega t. So that means your now omega, you may think that omega will be from 0 to infinity, but you can see so e to the power j omega t, e to the power j omega t is what? E to the power j omega t equal to cos omega t plus j sine of omega t. So omega t equal to say pi. So if you put omega t equal to pi, then what will happen? So omega t equal to pi, omega t equal to 0. Suppose omega t equal to 0, what is this value? Omega t equal to 0 means it is 0 This is J1. Okay. Omega t equal to 0 means 1. So again, omega t equal to pi. Omega t equal to pi means so omega t equal to pi. So omega t equal to pi. Again this will repeat. Omega t equal to pi. So that means omega t equal to, so if you take mod of this one, mod of Lj omega t, so mod of Lj L into mod of L of e to the power of j omega t. Repeat, mod of e to the power Lj omega t plot only to be taken for omega equal to 0 to pi by t. Okay, omega equal to from omega equal to pi by 2 to 2 pi by t, it will be mirror image, because omega t at that time it will be just cos pi. So all sine tan cos. So cos pi, cos of pi is again your -1. So just mirror image. So omega equal to 0 to pi by t. So from pi by t to 2 pi by t, it will be mirror image of L e to the power j omega t. Okay, mirror image of the earlier. Or if you take the mod value, then it will be same. That means it will repeat mirror image of Lj omega t from of the Lj omega t from omega equal to 0 to pi by t. Again from 2 pi by t to 4 pi by t, 2 pi by t to 2 pi by t to 3 to pi plus 2 pi by t to 3 pi by t will be same as 0 to pi by t, like that. Okay, so that means here only frequency response. This means in discrete domain. That means in discrete domain, in digital control, the frequency response of a gz equal to g of e to the power j omega t is important, is to be taken from omega equal to 0 to omega equal to pi by t only. So this is very important information. So there are many other things. This is the Bode. Those are the main difference between so you can Nyquist plot also you can do following this approach. That means Nyquist plot omega equal to 0 to infinity in place of, you have to write omega equal to 0 to pi by you have to take up to 0 to pi by t, and here omega equal to 0 you have to put, and then pi, then up to pi by t you have to put. Okay, and then you have to take pi by t to 2 pi by t. Okay, so 0 to infinity will not come in the picture. So this is about your board plot or black lead controller design. In this way you can extend. That means that the difference in board plot or Nyquist plot I have tried to say. There are many more things left in digital control. Digital control is one separate course is there for digital control. As I said, for MTech students, if you are interested, that you can take. There all these things are taught in detail. Again, lag lead controller, how to design, aliasing effect, all the things are taught in detail. Okay, so so I have completed all the portions that I am expected to cover in this semester. So thank you very much for your attention. So in the in the email, so you have raised, many of you have raised many very good questions. So I have tried my best to answer all those things. Anyway, so it is a very good experience to me also, that in this way I have taken class, and hopefully you have also enjoyed. Actually, in this pandemic situation, actually there was no other way to do. As you know, initially I thought that I will take live class, but I could not do because of the lag between my writing and my voice. So anyways, little bit, I think you have faced some difficulty in understanding, but I think if you go through my video and PDF files, you will later also you will see, you will understand its importance. Okay, thank you. Just I will go through once again if I have done some minor mistake. Okay, thank you.